Hello, welcome to another lecture. We are starting a new chapter. We're still talking about optics, but now we're going to examine light as a ray. We're going to look at the ray properties of light. And the purpose of this is to analyze the images made by optical devices like mirrors, lenses. Your eye is an optical device, and we'll talk about that in an upcoming lecture. So we saw in chapter 23 that the direction of light changes when it either reflects off of a surface or refracts into the surface, right, into the new material. It changes directions. And in geometric optics, we're going to take that information from the law of reflection and from Snell's law and combine it with a little bit of geometry to understand the images that are produced by the optical devices that the light is either reflecting or refracting into. And this is important because we use optical devices, optical instruments all the time, like our glasses, contacts, mirrors, right? Dentists use little mirrors to see the back of your teeth. And this kind of horrible looking picture here, right? It's illustrating that that our eye is actually a lens, and we sometimes need to do work on it, right, to get it functioning properly. So understanding how the eye works is a very important part of this chapter, and we'll get to that towards the end. What we're going to talk about in this lecture is mirrors, okay? So the simplest optical devices are reflective objects like mirrors or transparent objects like lenses. So today we're going to talk about mirrors, and then the next lecture we'll talk about lenses, and then we'll talk about optical devices after that. So we're going to use geometrical optics to explain the images produced. And what is geometrical optics? It's basically taking the laws of reflection and refraction, and incorporating some geometry. So just to wrap up, this was just like a motivation for our study in this chapter, right? We are going to be examining mirrors, which reflect light, and lenses are the refractors of light. They're transparent, so the light's going to go through. It's going to change directions due to the law of refraction, Snell's law. So let's first talk about the plane mirror, but before that, let's kind of like refresh ourselves, like what is it that we are seeing? Okay, well, like every day when I'm looking at my keyboard or my crazy dogs or a chair, what is it that I'm actually seeing? Well, our visual system can only detect objects that either emit light or reflect light. So objects that emit light are like the sun, a light bulb, right? Those are kind of like sources of light rays. But everything else, literally everything else, humans, chairs, trees, they're not creating light. They're reflecting it. They're reflecting it from the light source. So everything that we see, aside from light bulbs in the sun, is reflecting light, and that light ray is just ending up in your eye, okay? So we can't see things that aren't reflectors. And that's kind of the idea. There was some big news, I guess it's been several years, that the military is coming up with camouflage, right? An invisibility cloak. Well, how would we construct such a device? Well, it would need to be something that absorbs light rays and doesn't allow any to reflect, right? And then you would essentially be camouflaged. If something is not able to reflect light, then that light ray that strikes that object will never hit your eye, and you will never see it. Okay, it's interesting to think about. So, but of course, everything that we see it because light is reflecting off of it and entering our eye. So there's two types of reflection. Diffuse reflection is the type of reflection that occurs, from most objects, and that's because most objects are not like perfectly smooth. So you have a bumpy surface, and you're going to have different angles that the light will strike, right? Different angles of incident. And we know the angle of incident equals the angle of reflection, and that's based on the normal vector. So you kind of have slightly different normal vectors. I know these kind of look the same. maybe they're slightly tilted one way or another, right? And so then you're going to get different angles of reflection because of the different surface angles and different normal angles. So, and then the light ray is going to reflect off in different directions and maybe hit your eye, maybe not hit your eye, or maybe hit your eye in different places and end up looking a little bit blurry, okay? Flat surfaces, perfectly smooth surfaces, we call this type of reflection specular reflection. All the light rays come from the same, all the ones that come from the same direction are going to all reflect in the same direction because the surface is perfectly smooth. And so the normal vectors are all pointing in the same way, and therefore angle in equals angle out. So let's talk about how we locate an object, how our optical system, which is a combination of our eyes and our brain, locate an object. So we already talked about how the objects that we see are reflections of light rays, right? And the light ray is hitting your eye. So how do we locate an object? Well, what our eye and brain system has been trained or evolved to do is to take that light ray and trace it straight back, okay? In a straight line path. So we recognize that light travels in straight lines, and so our eye will and our eye brain system will say, okay, I see an object, it must be a straight line path, away from me, right? Not curved, not angled. And that explains why, if we think about that example we did in the previous chapter, where the apparent depth in a pool of water, right, where it looks shallower than what it actually is because our brain doesn't know that light refracts at an angle when it enters a new medium. So it's going to instead trace back a straight line, which is looking shallower than what the actual depth is. And this is kind of the same idea, right? Anything we see, our eye is going to automatically assume that light ray came from a straight line path away. And that's going to be an important concept when we look at images produced by mirrors. So let's throw a mirror into the mix and think about this. So instead of looking at an object now, we're looking at an image of an object in the mirror. So imagine I'm holding a ball above my head, so I can't see the ball. But what I can see is if I look straight ahead into the mirror, I do see an image of the ball, right? What is that? What am I seeing here? Well, my eye is going to get the light ray information, and it's going to trace that light ray straight back to the image, and it's going to say, oh, the image is over there behind the mirror, right? So when you look into a mirror, what you are seeing is an image of an object that looks like it's farther away from you, right? It looks like it's behind the mirror. And that's because our eyes are tracing that ray, and you can see this turns into a dotted line because this is called a virtual image or a virtual ray. And that's the ray that our brain kind of makes up into existence, right? That's why it's called virtual, in order to explain what it's seeing, right? In order to say, oh, you are seeing something, it's straight back, okay? So we define these kind of images formed by virtual rays. We call these virtual images because our brain is producing these rays, or it's kind of like connecting the dots, right? Taking that light ray straight back. And it's not real, it's virtual, right? So we call this a virtual image. Any image that is formed by virtual rays is a virtual image. So all images formed by flat mirrors, which we call plane mirrors, are going to be virtual images. And soon we're going to talk about curved mirrors, and some curved mirrors produce real images, okay? And a real image would be if the light ray, oh my God, why did my brain forget the word? Converges, right? Converges They're converging at a point here. That's where we place the image. So if this light ray converges on this side of the mirror, then it's a real image, okay? And we'll talk more about that. So let's look at a ray diagram. A ray diagram is how to determine graphically where an image would be, okay? So let's look at a ray diagram for a plane mirror. And the way we construct a ray diagram, I'm not going to be asking you to construct them, but I'm just going to kind of explain how they are constructed to help you interpret a ray diagram. So what you do is you draw 3 rays, and there's actually a better figure down here. So let me define some stuff, and then I'll talk about the ray diagram with these colored rays down here. So the objects in a ray diagram, we place on the reflective side of the mirror, right? And we let this object be like an arrow that has some height. And the height is called H0 or H0 or HO. Okay, whatever you think that is, it's an O. I realize it's an O now. So that's the height of the object. And we're going to place that object some distance, DO, away from the mirror. And then the image that's created is going to be given a height HI, and it's going to be a distance DI away. And constructing the ray diagram will tell us the location of the image and the height of the image based on where these rays all converge. Okay, you see they're converging to a point. So let's talk about how we do that in a ray diagram. So I like this picture because it has different colors for each principal ray. So there's 3 principal rays that we use to construct a ray diagram. And they all come from the tip of the object, okay, the height of the object. And when they all converge after we trace them is where the tip of the image will be, okay? So let's look at the first ray, the dark green ray. We're gonna draw it from the tip of the object at some angle, okay, going up. And, well, what do we know? We know that that ray is going to reflect off of the mirror and go that way, right? And the angle that it does that is going to be equal to the angle of incidence defined by the normal, right? We know that. That's the law of reflection. But if this green ray were to hit our eye, so say our eye is over here, ready to catch all those rays, okay? If that green ray hits our eye, where does our eye think it came from? Well, we got to trace that ray straight back. And that's where that ray turns light green, because it becomes a virtual ray, because no light exists on the non-reflective side of a mirror, right? Everything's getting reflected. But our eye doesn't know that. So we're going to trace back that dark green, okay, straight line path. Okay, and we draw that. And so then the second principal ray is going to, again, start from the top of the object, and it's just going to go 90 degrees to the mirror. Okay, it's just going to go straight from the object to the mirror, straight, no angles. And, well, what angle does it reflect? It reflects straight back, right? Comes in at an angle of 0 with respect to the normal, and it will reflect right back at an angle of 0 with respect to the normal, because incident angle equals reflected angle. But if that red ray were to reach our eye, where would our eye think it came from? It would think it came from behind the mirror. So we draw our virtual ray straight line path, okay? So now you can see we have two rays crossing. We have a convergence. We don't need to really draw at this point, need to draw the third ray, but we could. Okay, and for some curved mirrors, you probably need the third ray, but for this one we don't. But let's draw the third principal ray anyway, the purple one. So the purple one comes from the top of the object again, and it goes to the center of the mirror, okay? Because this mirror actually, extends down like this, and we're kind of just like half of it. So it goes to the center of the mirror, and angle in equals angle out, so it's going to reflect this way. And if our eye were to catch that light ray, where would it think it came from? We draw it straight back, right? It's going to think it came from straight back over here, and you can see that point where all 3 rays cross. That's going to tell us where the top of the image is, okay? And so then we can calculate the height of the image and the distance of the image from the mirror. And for plane mirrors, we will see that the image height and the object height will always be exactly the same. The image distance and the object distance will also be exactly the same, okay? Now let's talk about sign conventions. Okay, we're going to have some sign conventions for our mirrors, and you're going to see we'll have some for lenses too in the next lecture. So the sign conventions are that if the object distance is always positive, the object height is going to be positive if it's pointing up, okay? The image distance, if it's a virtual image, so if that image is formed on the non-reflective side of the mirror, behind the mirror, it's a virtual image, right? Because we had to create these pretend rays because that's all our little simple eye-brain optical system knows, right? We had to create these virtual rays in order to produce that image. And so anything that is on the behind the mirror is going to be the virtual side of the mirror. So DI will be negative, okay? However, the height of the image, if it's pointing up, it's going to be positive, okay? So I know the image is on the virtual side, but because the image is pointing up, it's also going to be positive, okay? So HO and HI will be positive because they're both pointing up, but DI will be negative. And so I talked about how plane mirrors produce images that are the exact same height as the object. Well, some mirrors that we encounter are going to magnify an object, and I'm sure you already know that, right? Because if you are if you have one of those cosmetic mirrors in your bathroom for either shaving or, for putting on makeup, you notice that mirror has like a curvature to it, right? And it magnifies your face. So some of these mirrors are going to magnify, but a plane mirror does not. But let's define the magnification equation right now. Anyway, the magnification equation is given by the ratio of the image height to the object height, okay, HI over HO. And you can see that for plane mirrors, since they're both equal, the magnification will be 1 for a plane mirror. The magnification can also be found by comparing the distances that the image and the object are from the mirror. And there's a negative sign though. Okay, so the magnification can also be defined with respect to the image distances, but we place a negative sign in front. And this equation is derived, with some crazy geometry, and I'll show you the picture for that, but I'm not going to subject you to that derivation. You're just going to have to take my word for it. So to wrap up this section, right, we talked about like where light rays come from, how our brain interprets where they come from, and for a plane mirror, it's a specular reflection, so they're all going to be reflected in the same direction. And if an object is placed in front of a plane mirror, then the image distance, right, is equal to the object distance. The image size is the same as the object size, okay? And plane mirrors always make virtual images, and light rays coming from the image do not actually pass through the image position, okay? They are virtual rays, right? The real light rays are not actually coming from there. Our brain is producing those rays because our brain thinks that every light ray we see comes from a straight line path straight back from its source, okay? So now let's introduce some curved mirrors, all right? And we'll talk a lot about the concave mirror, and then we'll talk about the convex mirror. So just in general, right, there's two types of curved mirrors. There's convex and concave. And there's some rules, there's some kind of like always true statements that we can say about convex and concave mirrors. And we'll kind of derive and walk through them. So for convex mirrors, well, they always, if you take a look at this picture, they always produce an image that's smaller than the object. Okay, so they always produce smaller images. Concave mirrors, well, they can produce there is no general. They can produce big, small, or equal size images depending on where you place the object. But for our purposes, the way we use concave mirrors is we use them always to blow up the image, okay? And so there's going to be a certain regime where we need to put our face or put our object in order to blow it up in the concave mirror, right? That's why cosmetic mirrors that are concave, you kind of have to be real close to see the magnification of your skin, right? You can't do it from far away. It doesn't work. So we're going to explore that. Plain mirrors will always produce same-sized images. Okay, so there's some general statements we can make about these mirrors. So let's get into a little bit like why are they like that? Well, this is a concave mirror, and we can draw, in general, the rays reflecting off of a concave mirror. So if we have incident rays all coming in parallel, and they're striking different parts of the concave mirror, well, what happens to the reflected rays? If we draw the normal, so let's draw the normal in these different locations, right? You can see the normal kind of rotates a little bit. And, well, if the normal is moving, then the reflected ray is also going to bounce off of it in a different angle. And what you can see is that for concave mirrors, the reflected rays converge, right? They're going to all eventually converge to a point somewhere over here, right? You can kind of see that. They're all going to converge. And that's an important reason why it's used as a magnifying tool. What about a convex mirror? Well, in a convex mirror, let's draw the normals to different locations. You can see they kind of like fan out. And so therefore the reflected rays are going to also fan out. And the reflected rays diverge on this side of the mirror. Where do they converge? Well, they're going to converge on this side, on the virtual side, okay? And so that's going to make sense when we look at some ray diagrams for the two types of mirrors. So we kind of been looking at both concave and convex mirrors. Let's now focus on the concave spherical mirror, okay? And let's define some points in general for curved mirrors. We're going to talk about a focal point. So the focal point of a mirror it's a point that lies along the principal axis, which extends straight through the middle of the mirror, okay? And the focal point is where all the light rays converge. And what we define like its distance from the mirror as the focal length. Okay, so the focal point is this dot. The focal length, little f, is this distance, okay? The center of curvature is another point on the principal axis. It's right here. And it has to do with the geometry of that mirror. So if we take that spherical mirror and we turn it into a sphere, the center of curvature will be the center of that sphere, okay? So the distance from the center of curvature to the mirror is actually the radius of the sphere. And there's a relationship between the focal point and the radius of the sphere, or I should say the focal length and the radius of the sphere. The focal length is always half of the radius of curvature, okay? So F is equal to R over 2. And this is true for all spherical mirrors, concave or convex. We're going to look at 5 cases, okay? We're going to use 5 ray diagrams to look at what kind of image is created by a concave mirror when we place that object in different positions relative to the center of curvature and the focal point, okay? So we're going to start off by putting the object far away from the mirror, and then we'll kind of bring it in closer and closer. So we put our object outside of the center of curvature and the focal point, okay? And we draw our ray diagrams. So we have our principal ray that goes straight across, and then this one, right, and this is the one that for the plane mirror came straight back. But for a spherical mirror, it does not, right? Because the normal of a curved mirror is not going to be parallel to that initial ray. It's going to be tilted at some angle. And so that ray is going to bounce off of the mirror and go down this way. Okay, angle in equals angle out. That's how you would know what angle it is. And the second ray we're going to draw, sorry, that's my robot vacuum. The second ray we're going to draw is going to go to the center of the mirror, okay? And it's going to bounce off, angle in equals angle out, and it's going to go this way. And you're going to find the place where those rays cross, and that's going to be the top of your image. And you can see here, conversely from the plane mirror, for this particular case of a concave mirror, the image is actually formed on the real side, isn't it? The image is on the real side of the mirror. So if we were to stand in front of a concave mirror and we were to stand outside of the focal point and outside of the radius of curvature, what we would see is ourselves. We would see a shrunken version of ourself, and we would see an inverted version of ourself. And it would look like we are not behind the mirror. It would look like we're closer. Okay, it would look like we were standing upside down on our side of the mirror. Okay, so the image produced by an object located here is going to be inverted. It's going to be located between the radius of curvature and the focal point, and it's going to be smaller than the object. And the image is going to be real. Okay, so these are the qualities of the image produced by an object being placed outside of the radius of curvature and focal point. Okay, so that's case number one. Now let's bring our object a little bit closer. Okay, let's place our object at the center of curvature. What happens? When we do that, we draw our principal rays, and you can see that they are going to end up converging at the exact same distance that the object is. And so what we see in the mirror then is we see ourselves inverted again, but we're going to be the same size. Okay, so the size of the object will equal the size of the image, and then the distance of the object will equal the distance of the image. That image is still real because it's located on the real side of the mirror. Okay, and it's not magnified. M equals 1. For case 3, let's move the object a little bit closer. So now we're placing the object in between the center of curvature and the focal point. And when we do that, we draw our two principal rays. We only need two. And where they converge is past the object. So we're still on the real side. They converge past the object. So the image looks like it's farther, or looks like it's behind us, really. Right? Like as far as distance goes. And it's inverted again. And it's also real. So it looks like it's on the real side of the mirror. Right? So the image is real, the image is inverted, and it has moved farther away from the mirror. Case number 4, let's place the object on the focal point. If we place the object on the focal point, something interesting happens. The light rays no longer converge, okay? Because they end up being perfectly parallel to each other. And so they will never converge, right? If two parallel lines will never cross, right? So they're never going to converge. And therefore, we don't see an image. And that's why we look like a big blurry mess in the mirror. And that's when you're holding that concave, cosmetic mirror at a weird spot, you're just blurry, right? So it doesn't really help you like do whatever you were going to do to your face. You have to bring it like a little bit closer in order to see yourself correctly. Okay, so like this, right? Now, when we bring our face or we place the object between the focal point and the concave mirror, we finally see ourselves upright and we see ourselves magnified, which is the purpose of the concave mirror. And this is because when we draw our principal rays, the light rays, again, they don't converge on the real side, but because they're not perfectly parallel, they do converge back here when we trace our virtual rays back, because our eyes are going to be over here looking, right? Our eyes over here looking at these rays, and it's like, where do these rays come from? Well, let's trace it straight back and see, right? And so our eyes are going to think that this image is behind the mirror, and because they converged up here, that image is going to be magnified and upright, which is the purpose of a concave mirror, right? To magnify something. And so finally we get an upright image. It's magnified and it's virtual, right? It's a virtual image because it's behind the mirror, right? The light rays had to converge behind the mirror. So those are the 5 cases for a concave mirror, okay? Because remember, concave mirrors, like they can produce any kind of image, right? They can produce virtual and real. They can produce magnified or shrunken, okay? And so that's why we kind of explore all the different cases. But for convex mirrors, as you're going to see coming up, they only really produce like one kind of image, and we'll talk about it. So let's look at this got the concept. So based on what we just, like the qualitative aspects of the image produced by a concave mirror, let's look at a spoon. We have a shiny spoon. It's kind of spherically shaped, right? One side is concave, one side is convex. And let's say that we look at our reflection from the concave side of the spoon. Okay, so we're looking at ourselves, and here's like a gigantic spoon. Okay, we're looking at the concave side of the spoon. And what we notice is that when we hold the spoon at arm's length, our picture or our image is upside down. Okay, our image is upside down and appears to float in front of the spoon, which means it looks like our image is upside down, but between us and the spoon. And then we bring the spoon a little bit closer. We hold the spoon about 6 centimeters from our eye. When we do that, we only see blurriness. We only see a blurry reflected picture. And then we bring it even closer, about 4 centimeters from your eye. And finally, our picture turns right side up and appears to be behind the spoon. Can we use those 3 qualitative pieces of information to determine the focal length of the spoon? So think back to these pictures, right? And remember, when things got blurry, that's when the object, ourselves, was located at the focal point, right? The focal length. The object distance was equal to the focal length. And so we got a blurry picture. When we held the spoon at 6 centimeters, we got a blurry picture. Boom, we know the focal length, right? So you can determine the focal length of your bathroom mirror, your beauty mirror, by moving it in front of your face and seeing when your face turns blurry. And if you can kind of guesstimate that distance, that's the focal length of your mirror. And in order for that concave mirror to be useful, you need your face to be in between the focal length and the mirror, right? For your picture to show up upright and magnified. So in summary, here's all those ray diagrams that we went through, from increasing to decreasing, or from high to low distance, right? We brought that object closer and closer to the mirror. And here's the properties. So this is a very nice summary of everything we just talked about. Okay, and so to wrap up, right, we talked about the qualities of the image produced by a concave mirror. And that's basically what all the summary is saying. So I'm not going to repeat it. We just talked about it, okay? And you can read through that. So we talked qualitatively about the image produced by a concave mirror. So let's quantitatively determine the distance that the image is from the mirror, whether it's upright, whether it's magnified, if it's virtual, if it's real. Okay, let's use some equations to figure that out. And then they're quite simple. This very crazy diagram is the proof or the derivation of this very simple equation. So I just threw it on here just so you could see some geometry was used, okay? And what that geometry told us is this, that 1 over the distance the object is from the mirror plus 1 over the distance that the image is from the mirror equals 2 divided by the radius of curvature of the mirror. Okay, little r, big R, doesn't matter. I don't know, by habit, I write big R, but the book uses little r. Same thing. And the focal length is related, as we saw earlier, right, is related to the radius of curvature of the mirror. The focal length is r over 2. And so we can rewrite that equation in terms of f. And we see that 1 over dO plus 1 over di equals 1 over the focal length. Okay, you can use either one. Either one's fine. Either one's fine. And the second equation that you're going to use a lot, and I just wrote it right here, right? You're going to use these in tandem, the magnification relationship, okay? So you'll be using those two equations together to solve these problems. There's sign conventions again, okay? There's going to be a lot of sign conventions. So, and they're the same for mirrors, okay? So all mirrors have the same sign conventions. Focal length for a concave mirror is positive. And why is that? Because the focal length and the radius of curvature is located on, well, I just drew, that dot is not the focal length. The focal length is probably right here. The focal length and the radius of curvature are on the real side of the mirror, aren't they? Right? Because a concave mirror is shaped like this. So the center of that sphere is on our real side. It's on the reflective side. So its value is going to be positive, right? The object is always placed in front of the mirror, so its distance will be positive. The image distance, we saw that the image can be real or virtual for concave mirrors. So if it's virtual, then the distance is negative, okay? If it's real, if it's on the real side, then the image distance is positive. So this is kind of the derivation of where the magnification equation came from. Okay, so just kind of just showing it to you, right? And there's the magnification equation that we already talked about. And here's a table with the sign conventions for both types of mirrors. So we haven't gotten into convex mirrors yet, but we will. But here's for concave mirror. Okay, it's positive for radius of curvature. Focal length is positive for a concave mirror. The image distance is positive if it's on the reflective side. It's negative if it's on the back of the mirror, the non-reflective side, right? Then it's a virtual image. The image height is positive if it's upright, negative if it's inverted. And then the magnification is positive if the image is upright, and then the magnification would be negative if the image is inverted. So let's do some examples, and then we'll talk about convex mirrors. So let's kind of put this into practice. So we have an object that is 1.5 centimeters tall. So what's that? That's HO, right? Height of object. It's placed in front of a concave mirror that has a radius of curvature of 20. So R will be equal to plus 20, right? Because radius of curvature is positive for concave mirrors. We are asked to find the image distance, so we need to find DI. And the height of the object, so we need to find HO. No. Image distance and height. Sorry, image distance and height. So we need to find HI. If the object is 14 centimeters from the mirror, so that's DO. So we're given two possible DOs, and we're going to find DI and HI. So we're going to need our two equations, the magnification equation. Okay. We're going to need our, since we're given the radius of curvature, I'll use this version of the mirror equation. All right, so we're going to need those two. And then draw a ray diagram. So what I'll do is we'll just go up and look at the ray diagrams that I had posted. Okay, we'll go look at that when we get there. So let's do part A. So our knowns are HO is 1.5 centimeters. And if you take a look, everything is given in centimeters, so you don't need to convert anything. Okay, you can go ahead and keep doing all the math in centimeters. Your answer will be in centimeters. Okay, so we don't have to convert anything. Our radius of curvature is 20. Our DO is, for part A, 14. So can we find the image distance and the height? We sure can. We do have enough information for that. So 2 over 20 is going to be equal to 1 over DO, which is 1 over 14, plus our unknown. So we can solve for DI. 2 over 20 minus 1 over 14 will give us 1 over DI. So 1 over DI is 0.0285. I'm just writing a bunch of decimals, okay? And that's units of cm to the -1. I need to solve for DI, so I'm going to have to take the inverse of that, right? So don't forget, it's a very common mistake to forget the inverse and you give me this as your answer. That's not the correct answer. So 1 over that is the correct answer. That's 35. So the image is 35 centimeters from the object. From the mirror. It's 35 centimeters from the mirror. And it's a positive value, isn't it? So that means it's on the real side of the mirror. What about the height of the object? We can use the magnification equation to figure that out. Well, we don't know the magnification, but we do know the two distances, don't we? So HI over the height of the object, 1.5 centimeters, is going to equal negative image distance, 35, over object distance, 14. We can solve for HI. Negative. And we get 3.75, negative. So the image is inverted, isn't it? It's upside down because its height is negative. So the image is inverted and it's located 35 centimeters from the mirror. Draw the ray diagram. So let's go up to our 5 cases and let's see which of the 5 cases this is. Well, we can figure that out by looking at the image distance in comparison with the radius of curvature and the focal length. So let's write down what the focal length is. The focal length is half the radius of curvature, right? Let me write that one down. So the focal length is 10 centimeters. And 14 is in between 10 and 20, isn't it? So that means our object is placed in between the center of curvature and the focal length. So let's go and look at that ray diagram and see if it matches what we found for DI and DO. So we're in between the focal length and the radius of curvature. That's where the object is placed. So let's scroll up here. Let's look here. So which one of these is that? It's this guy right here, isn't it? Nope, that's the image. Here he is, object, right? We're looking for the object placed in between C and F. So let's pull that down here. And so instead of drawing the ray diagram, we're just kind of like gonna take one. Okay, so our object is placed between C and F, and sure enough, our image is on the real side, so it's positive, check. It's farther away from the object, right? Our image is 35 centimeters. Our object is 14, so it's behind. That makes sense. And our HI was negative, and our image is inverted. So it all checks out. We did our math great. Okay, so what I'm going to do, just so this video isn't like super long, I'll let you guys do part B. All right, and do it. You're going to follow the same steps. Do part B and go up there and check which case that part B lines up with, and that your math lines up with the ray diagram. Okay. So I think I have got the concept here. Okay, so let's say we have an object placed 12 centimeters from the concave mirror. So that means our DO is 12. And the resulting image is real. Okay, so DI is positive. And it's 2 times as large as the object. So what does that mean? That means that HI is 2 times as large as the object's height, right? Can we find the focal length of the mirror? So, well, what is the focal length of the mirror? It's 1 over DI plus 1 over DO. And, well, we know DO. DO is 12. Do we know DI? I mean, not really, no. We know it's positive. So can we figure out what DI is so that we can find the focal length? Well, we do have this. So let's use our magnification equation to figure out what DI is. So HI over HO equals negative DI over DO. And we have a relationship between HI and HO. So if I plug that in here, we have 2HO in the numerator and HO in the denominator. Okay, solving for DI, and then our DO is 12. So let's pause for a second, because we are now able to solve for DI, right? But what I'm seeing is I'm seeing a negative sign here. And when I solve for DI, I'm going to be getting a negative value. However, what did the question tell us? The question told us that the resulting image is real. So shouldn't DI be positive? What happened? Well, we made an assumption, didn't we? When we used this box equation, we made an assumption that the image height and the object height were both upright. But that was an assumption, and that is actually not correct. Because if the image is real for a concave mirror, okay, let's go to our cases here. If the image is real for a concave mirror, what did we see? Image is real, image is inverted, image is real, image is inverted, image is real, image is inverted. Image not there. Image is virtual, image is upright. So for a concave mirror, anytime the image is real, it is also inverted. So we must update our equation that we use to relate HI to HO. Okay? HI should actually be equal to negative 2HO. And so when I plug that negative in, now our negatives cancel. And when I solve for DI, I'm going to be getting a positive value. Okay, I'm going to be getting positive 24. Okay? So that's kind of like why this is a got the concept question, right? That's the concept. The concept is whenever a concave mirror gives you a real image, that image is inverted. Okay? So now I have DI as positive 24. So we can solve for we can solve for 1 over f. So 1 over 24 plus 1 over 12, well, that is 1 over 24 plus 2 over 24, right? Which ends up being 3 over 24. And to solve for f, we need to invert that. So f would be 24 over 3, which would be 8 centimeters. Okay, so the correct answer is 8 centimeters. So there was like a hidden concept in there, right? We kind of took this phrase for face value. We said 2 times as large, but it can be 2 times as large, but be inverted, right? So this is a very, very good question to review. So to wrap up, we used the mirror equation to relate the focal length or the radius of curvature to the image and the object's positions, right? And we applied the sign conventions properly. And we also, from the got the concept, right, had to really think about where this object is. And the piece of information they gave us was that because the image was real, we had to go back and look at our ray diagrams and make sure that we understood that whenever we have a real image produced by a concave mirror, that image is inverted. And so when we applied the magnification equation, we had to make sure that we were writing our HI as a negative, okay? So let's talk about convex mirrors. Convex mirrors, a lot simpler because there aren't as many different cases, okay? So a convex mirror always produces an image that is smaller than the object. So if an object is held next to a convex mirror, the resulting image is smaller, and this is illustrated here with this picture, right? So let's say you and your loved one are in Paris and it's so romantic and you're looking into each other's eyes and you happen to see a reflection in their eye and you see the reflection of a gigantic building like the Eiffel Tower and it's so small, right? The reflection on the eye is so small. And well, that's because your eye is convex, right? Your eye is like a sphere, and the reflective side is, we're looking at the outside, okay? So now here's a little diagram of a convex mirror. The reflective side is now facing, this way, right? It's bulging out. It's convex. And therefore, the focal length and the center of curvature are over here on the virtual side, aren't they? So the virtual side having the focal length means the focal length is going to be negative for a convex mirror. And it's negative because when we draw our ray diagrams, what we see is that the light rays on the real side never converge, right? They point out. So when our eye is over here looking at those light rays, okay, converging or diverging, I should say, our eye is going to trace them back and it's going to make them converge on the virtual side. So what this tells us is that the image that is formed by a convex mirror is not only, smaller, always smaller than the object, but it will always be a virtual image. Okay? And it will always be upright. So convex mirrors have some special properties. So let's place our object. It's going to do the same thing we did for concave mirrors, except, there's going to be less cases. Let's put an object far away from a convex mirror and kind of see what happens. So when we place our object far away from the convex mirrors, we are going to draw our principal rays. And when we do that, you're going to see that when they reflect off the convex mirrors, they're going to diverge. And our eye is going to trace back, right? Our eye is going to be looking at these rays and going to be tracing them back to a point on the virtual side. And the farther away the object is, the smaller the image will be. Okay? If we were to move the object a little bit closer to the mirror, the light rays are still going to diverge, but they'll form like a slightly larger image, but the image will still be smaller than the object. Okay? Convex mirrors always make objects appear smaller, and therefore they provide a wide angle view. And that's why we use convex mirrors in vehicles, right? We put them in our rearview mirror. We put them on the side mirrors because we want a wider field of view to see behind us when we're driving for safety. So that's why there's also a label on the passenger side mirror, and the label says objects in mirror are closer than they appear, right? Because look at the distance from the image to the mirror, right? It's closer than the object is to the mirror, right? So they look closer than they actually are. So we looked at some qualitative properties of a convex mirror, and there's a lot less combinations available for the image. The image will always be virtual, it will always be smaller, and it will always appear closer to the mirror than the object is. And they'll always be upright. So there's a lot of always here. Okay, and it's summarized right here. The same equations that we use to quantitatively determine image and object positions, or not object, but image position, image height, we're going to use the exact same equations, but we need to apply the new sign conventions applicable to convex mirrors. Okay, we're still going to use the mirror equation. We're still going to use the magnification equation. And in this picture here, this is all the ray diagram and all the geometry that proves to you that these are still valid equations, okay? And where 1 over f can be substituted for 2 over r. Same equations, okay? Sign convention, so we gotta be a little more careful now. The radius of curvature and the focal length are negative for convex mirrors, okay? Everything else is still true. If the image is on the reflective side, it's positive. If the image is on the non-reflective side, it's negative. And remember, for convex mirrors, the image will always be in the virtual side, so the image distance will pretty much always be negative for convex mirrors, okay? However, for convex mirrors, the image is always upright, so the image height will always be positive, okay? And then the image will always be shrunken compared to the object for a convex mirror. So our M will always be less than 1 for a convex mirror. For a concave mirror, it could be like either way. Okay? So now let's do an example like we did before, but with a convex mirror. So we have our same object height, 1.5 centimeters. And it's placed in front of a spherical convex mirror that has a radius of curvature of magnitude 48. Telling us that we need to make sure that we include our negative sign because the radius of curvature is negative for convex mirrors. So we still want to find DI and HI. Okay, same procedure. We're going to use 2 over R equals 1 over DI plus 1 over DO And when we substitute our r, it needs to be negative. So we're going to have negative 2 over 48 equals 1 over di plus 1 over 68. We're going to solve for di. Negative 2 over 48 minus 1 over 68 will give us 1 over di. So that value ends up becoming, oops, be careful when you type this in your calculator. You got to put parentheses or else your fractions could get all wonky, right? Like that just happened to me. So I get negative 0.05637. I'm going to inverse that to get the di. And I get negative 17.7 centimeters, okay? My di is negative, as it should be for a convex mirror, because convex mirrors always produce virtual images. So di should definitely be negative. And what about hi? So I'll use my magnification equation, which is hi over ho equals negative di over do. Let's plug in all of my knowns. So I get, solving for hi, ho is 1.5. di is negative of negative 17.7. do was 68. Okay, when I solve for hi, I get positive 0.39 centimeters. Okay, so my hi is positive, which means it's upright. All right, upright image. Smaller than 1.5, right? So it's upright and it's shrunken. And it's virtual. So notice how it didn't ask us to draw the ray diagram here, because it's kind of, they're all the same, right? Because a convex mirror produces the same qualities of an image. It's always virtual, it's always upright, it's always shrunken. So this would be one of the ray diagrams for that, okay? Doesn't matter where that object is placed. I'll let you do part B, okay? You should get the same qualities. You should get a virtual image. You should get a shrunken image. And it should be, let's see, virtual, shrunken, upright. And it should be upright. Okay? Let's do this last got the concept, and then we'll be all wrapped up for this lecture. I know it had some obnoxious background noises, and I appreciate you guys sticking with it. Okay. So if the image is made by a convex mirror of focal length f, if that image is half the height of the object, then what is the distance from the object to the mirror? So let's write everything down. So the image height, hi, is half the object's height, right? And the focal length is f. And the question is, what is do? Okay. So what's do? So here's our 1 over f, 1 over di plus 1 over do. We're solving for do. We don't know di. We know that f is f. Okay, so what is di? Can we figure out what di is? Yes, we can, because we know this relationship and we can use the magnification equation. So when we do that, hi is 1/2 ho. And negative di over do. But what do we know about the image produced by convex mirrors? We know that di must be less than 0. So my di should be negative, and that negative will cancel with that negative outside, right? So let's think about that when we solve for di. So I solve for di. These guys get eliminated. and I get 1/2 equals, I'm going to get rid of that. It's going to be negative di over do. So 1/2 do will equal di. Okay? And so what I want to solve for do, so I'm going to substitute for di. I'm going to get 1 over f equals 1 over 1/2 do plus 1 over do. Actually, I'm thinking maybe the negative, I should not assume. Yeah, I wanted to like and put that in there, but I'm thinking now when I'm looking back, I don't think we should pull the negative out of the di, right? I want to do that here because what I want to make sure that is happening is that I'm getting a negative number for this term right here. Okay? So I actually I don't want to put my negative here yet. So let's not do that yet. Let's leave it implied inside. Okay? So then that means di would be negative 1/2 do. And so I'm going to plug in my negative there. And that makes sense, right? Because di should be negative. And I know that do is always positive. So di should be negative 1/2 do. Right? Are we on the same page? So now when I add these two numbers together, I'm adding a negative to a positive, as it should be, because di is always negative for convex mirrors. So now when I solve for do in terms of f, so this 2 is going to come up, isn't it? And I get 2 over do plus 1 over do, which gives me negative 1 over do equals 1 over f. And so my do, what is do? I can do all my inverses, right, if I want to, but I can just see here that do is equal to f, right, because f is negative. And here they give us our answers in terms of absolute value of f. So either way, we get f as do. Okay, so this was a good Got the Concept. That's all I had planned for today. We covered all the mirrors, so the next lecture we'll be covering lenses. And what you're going to see is that these sign conventions are going to flip-flop, okay? So just be prepared for that. All right, have a great day.